Okay, so let's compute the first average of the second term. Okay, and to do this, so what are we going to do? So let me just say what we're doing. So we want to compute is so this is here we want to compute the expectation. Okay, so we have the tuple of these kind of different exponent things here, and then we're going to take the difference of these. Okay, so we're going to compute this expectation. So this is what we want. We want to know what this is. All right. So to compute this, there's some preliminaries that we need to cover. So we need some things. So we need stuff. Okay. So so preliminaries. So first, so we need to talk. So multiplying random variables. Okay. So there's kind of a formula for independent random variables, and that is if you take the expectation of when I multiply these all out. Right, so this is just the expectation of a single random variable to the nth power. Okay, this is the first thing. The second thing that we need is Jensen's formula that we'll use. Right, so what does Jensen's formula say? So it says that, so there's kind of two versions of it. So convexity, so it's an inequality, right? There's a convex version and there's a concave version. Then I'll give the formula. And then we'll give an example of such a function. Okay, so convex functions, these are functions where this second derivative is non-negative, and then these are second derivatives are less than or equal to 0. Okay, and then so what does the formula say? The formula says that in the convex situation, the function of the expectation is less than the expectation of the function. Okay. Okay. What's a function that does this? The exponential. Okay. It's the opposite for concave functions. That is, the expectation of the function. We expect this to be less than the function of the expectation. Okay, and so here the classical example is the natural log. Okay, so these are the two formulas. These are the formulas here. Okay. All right, so those are the two formulas that we need. So one thing you can do with these is you can put, for example, you can relate multiplicative and arithmetic averages. Another thing you can do is you can so like an application. So one thing you could look at is you could write things like here log of x. So this is less than or equal to the expectation of x is less than or equal to log of the expectation of the exponential of x. Okay, so this is something that you can do. Okay, so we're going to use this, and all right, so we're going to use these properties. All right, and so there's an auxiliary definition. We're actually going to have a couple auxiliary definitions like this. Okay, so let me just say that we're actually going to do both averages, right? So here, the first, so let's do both averages. So the second average, okay, so this is kind of the end result here. Sorry, that's not right. All right, so we do this, the L1 norm, the first vector, the L infinity norm here. So this is going to be less than or equal to L plus 1 over 4 of some sort of average different at P. So this is the pth part here. So this is the result that we'll have, like so. So this is the result. All right. And let me explain this auxiliary quantity. Okay, so what we'll do is we define the average different over a prime. So the idea, this is like the average different order at P, right? This is equal, we're going to define this to be the thing given by, okay, so it's going to be P diff over P, like so. Okay, so we raise it to a power, then we take the expectation, and then we take the log of it. Okay, so that's our definition for this average different. Okay. Okay, so let's compute the first average of the second term. Okay, and to do this, so what are we going to do? So let me just say what we're doing. So we want to compute is so this is here